Good morning, everyone. Thank you for attending. I appreciate your time this morning. I know these webinars are informative to some, and I hope they are to you also. I hope you have a fresh drink in your hand and you're a comfortable chair to enjoy this with. I expect there's going to be a few more people join us as we get started here, but there's no reason not to start on time. So on we go. In the beginning here, I want to let you know that I'm going to answer as many of your questions as possible at the end of the presentation. Please submit your questions at any time, though. I know questions get forgotten if you don't ask them when you're thinking about them. So please, whenever you're ready, ask your question. Our chief engineer, Daryl McCulloch, is gathering the questions during the webinar, and at the end, he's going to provide us with the questions and probably some of the answers at the end of this presentation. For those of you who haven't met me yet, my name is Tom Haber, and I lead some of the best non-metallic equipment inspectors in the world. I've been involved in the FRP industry for over 30 years now, and I've had the opportunity to supervise the fabrication and installation of several large FRP projects, including power plant stack liners, flue gas desulfurization ductwork, chemical process piping, and a bunch of FRP storage tanks and pressure vessels. During this time, I've also had the opportunity to witness a lot of pressure tests and acoustic emission tests, along with performing many hours of ultrasonic testing on equipment. I am still the chairman for the American Welding Society's G1 Committee for Thermoplastic Welding. I'm also the current chairman of the Fabrication and Examination Subgroup for the ASME NM2 Piping Standard, and I'm a member of the ASME RTP1 Standards Material and Quality Assurance Subcommittee. So I get around a little bit. But enough about me. I'll take a few minutes here and have you all introduce yourselves. Oh, no, I'm just kidding. Sorry. This is a one-way discussion today. Again, we do highly encourage questions. Questions are one way that we get feedback from you, and we make sure that we tailor these webinars to what the public needs, what the public's asking for. So in order to ask a question, how do you do that? Well, you're going to activate the questions panel by clicking on the arrow to the left side of the tab. Your pane may look a little different than mine, but all the questions are going to be private, sent directly to Daryl, and we will not use names when we use the questions unless you specifically ask us to. This will allow us to gather everyone's questions and then combine similar questions so that we can get to as many as possible after I've gotten through the slides. The slide numbers aren't listed, so you'll just have to send your questions when you think about them, and hopefully we'll be able to understand. So this presentation is going to discuss a lot of different standards and a lot of different pieces of equipment, because you could do a presentation strictly on the piping standards, and you could do one strictly on the vessel standards, and you still wouldn't be able to fit it all into a 40-minute presentation. So my goal here is to be top level, to give you an understanding of what the specifications are, where their strengths and weaknesses are, and where you might consider using them in your projects. There's a lot of knowledge in these specifications. A lot. And there's a number of specifications around the world that are in use. There was no way for me to pick every standard that mattered to everyone and compare and contrast them. That would be a research paper for some brilliant young engineer somewhere. So I encourage those of you with big companies or maybe MTI membership. I think they've already done the vessel review, but similarly. My goal here is to explain as much as I can anyway, a top level view of these specifications. And I want to mention here early in that you're going to hear me say specifications. I know some of these are codes, I know some of these are standards, and I know some of these are product specifications that are listed here. I'm using the term specification globally as a global answer for all of them. I look at all of them as if they are product specifications for a product. Some are codes, some are standards. So When you hear me say specifications, please don't send a lot of questions saying this one is a standard and this one is a code. I understand that. I'm trying to be a little more top level here. Okay. You see the standards that I've considered at the bottom there. Primarily, they are the prominent ones used most that I'm aware of in Europe and America. Obviously, I don't know all of the ones used around the world, but I know these are used fairly regularly around the world because we do some work also around the world. So, just for your information, those are the standards we're including. I'm going to start with the piping standards because an overview of them is way different than the vessel standards. There's a lot of things in these piping standards that are similar, and those similarities are places where you can be comfortable that all of the standards will provide you guidance. So all of these specifications have some level of piping and fitting design included in them. The ASTM specifications primarily focus on the piping and the components, not necessarily the assembly of it all. The other specifications do a better job of including everything. Now, they all have some level of material handling requirements. Fiberglass materials are sensitive to moisture and heat sometimes too. So the material handling of all these items is important, and that's why it's important. That's why it's in all of the specifications. All of the specifications also require some level of product testing. The ASTMs don't really require product testing as long as you use base factors, base known properties for the materials. That's hand-laid material, so the properties of a hand-laid material are pretty well known at this point. And if you use the safe design factors there, you don't really have to prove anything with that. And some of the standards require a full hydrostatic design basis test of the pipe before you can design with that pipe. So to give you an idea of the different level of requirements on the design. All these product specifications are good for producing consistent quality, recognizable, repeatable pipe and fittings. Where they differ sometimes is whether they're good for building custom projects. And that's where you need to be more careful. So what are the differences, the unique items between the standards? Well, only the NM2 and the ISO 14692 specs contain the reference forms for the vendor's QA/QC program to be able to track raw materials, to input data based on testing, things like that. So those two standards will provide you all of the basic forms and explanations, how to use them, and that's one of the things that sets them apart from the other standards. There is also a big difference in the quality control requirements shown in these documents. The ASTM specifications generally refer to other ASTM specifications, and there are some requirements in some of those. You just have to be able to gather them all, put them all into your specifications, and make sure that you've applied them for your project. The ISO 14692 and NM2, however, do have some of the most stringent QA/QC requirements out there. And they all have requirements for raw materials through their use and include product testing of the materials that are produced. These specifications all provide methods for determining pipe and fitting thicknesses, especially for common pressure and sizes and diameters. But very few of them provide good information regarding the overall system design. And that's where the NM2 and the ISO 14692 have a better strength because they do a better job of looking at the overall system and not just the components. And when it comes to supporting of FRP piping, that's one of the most critical things we've found. I'm blessed to work with some smart engineers, and as an ex-fabrication guy, I just always assumed that there was something wrong with the fabrication. But I have learned in my time here that sometimes engineers make mistakes too, or don't do their due diligence and complete the whole job. So if you're going to have a piping system made out of non-metallic piping, your supports are going to be different, or they should be different if you want a good long-term project. Delve into each standard a little bit to try to give some of my impressions of each standard here. The NM2 FRP piping standard contains requirements for piping and piping components that are produced using glass fiber reinforcements embedded in cured thermosetting resin. That's all fancy way of saying strands are wetted out, or reinforcement material is wetted out with a resin and then applied to a mandrel and allowed to cure. The standard allows for piping up to an internal pressure of 250 psi, and similar to ASME Section 10, the pressure vessel code, it's limited to an internal diameter being less than the pressure multiplied by the diameter has to be less than 7,200 psi G inches. So that's the framework for the maximum size and pressure capability. So it will handle 250 psi in smaller piping, and as you get larger piping, it doesn't relate to that. It does not include piping being used as ductwork or with a pressure rating within 1 psi of the pressure in the surrounding atmosphere. This standard is intended for pressure piping and not ductwork. There are other standards out there for ductwork. So, some good things about the NM2 standard. It does include the requirement for bonder certifications. Bonder certifications are important in fiberglass because they're like welder certifications in metal. You wouldn't ask someone who doesn't have a welder certification for titanium to weld your titanium vessel. So it's always a good thing to invoke requirements for bonder certifications. That proves that the vendor has done some training, some work with the bonder, and that bonder actually has an understanding of what needs to be done. NM2 provides and requires the use of material tracking and test forms be used. The proper use of these forms will provide the end user with proof that the right materials were used, and that the fabricator paid attention along the way and did this due diligence. One of the design methods available within this standard allows for the use of long-term test data to provide lower safety factors for fabricators who have performed this valuable testing. So this is basically the HDB testing that's talked about a lot in other standards also. And it's a long-term test that is used then to equivalate longer-term service. It's, I think, a 14-month test that then is equivalated out to 20 years or better. What to expect from that piping system. So when you have that data, it provides you very good information on your actual pipe and fittings that you can use in your design and should allow you to use lower safety factors. And again, one thing I want to mention, because supporting is very important to FRP pipe, the proper isolation of movement, the proper use of an anchor in a right location or a guide to make sure that the piping is doing what you want it to and it's not trying to blow off its end elbows is extremely important, because you can buy all the right piping and all the right fittings from the best fabricator in the world. But if you're not holding the piping still and it's just hung by ropes the first time you pressurize it, you're going to see impressive movement in that piping. So NM2 does a good job of providing guidance on how to support piping and how to properly keep it from tearing itself apart. The ISO 14692 standard. It's actually a group of piping standards that contain rules to govern the design, fabrication, materials, erection, testing, everything of fiberglass piping. The standard covers all the components from design, fabrication, the fabrication of the piping, the components, the assembly of it all. It includes rules for tees and reducers and flange joints. It is an exceptional standard that has a lot of good information in it. The qualification and manufacturing of FRP piping, system design for FRP piping, all of that is in there. And again, this being one of the most robust and complete standards that's out there on the market, the only drawback to it is that it is very robust and very knowledge driven. You have to understand some FRP piping. You also have to have HDB testing, because ISO 14692 only allows long-term testing to determine the piping properties. Again, this test takes roughly 14 months, and it does provide valuable data. but it also eliminates a lot of non-commodity pipe fabricators from using this specification. It's not a big deal because you want good pipe, you say, and I agree with you, but there are good vendors who won't be able to qualify for this that you will exclude from your vendors list. Just understand that. ISO 14692 also includes bonder certification requirements. Again, bonder certification is extremely important for fiberglass piping for the reasons I explained before, but it's often overlooked. So both of the standards, NM2 and 14692, require bonder certification and the use of a bonder procedure specification that's acknowledged and that's recognized and understood. So the standard also provides for material tracking and testing forms. This, again, and NM2 both provide the forms to the vendor that they require to use, so they don't have to come up with their own forms if they don't want to. So it is fabricator friendly. It does have an extremely detailed design section. However, again, you have to have the HDB testing to be able to do this. ISO 14692 is very well suited for ensuring that the piping components produced to this standard are consistent. And so it's used for a lot of the commodities type piping that you'll see out there. It does work for custom piping also, but again, you have to have the HDB. So custom is a relative term with ISO 14692. It does also provide some details for the overall system design and how to support the system. It doesn't go as well into how to design the supports as NM2, at least in my opinion, but it is a very good standard and is used well throughout Europe. Brings me to a couple of the ASME B31 standards. There are two of them, B31-1 for power piping, power plant piping typically, and B31-3 for process piping, typically used in chemical facilities or other processing plants. The B31-1 covers fiberglass piping using an mandatory appendix N. This is where they provide the unique requirements different than the metal requirements shown throughout the rest of the book. B31-3 has a lot of good information on thermoplastic bonding, and thermoplastic information is not found in other places. So the ASME B31-3 discusses the specific rules for their non-metallic piping, though, in Chapter 7. The difference here is that ASME NM2 was basically designed around fiberglass piping, period. That's what that standard does. In both of the B31 standards, the only weakness with them is that they're basically developed for metal piping, and then fiberglass piping was added into them, and then you have to be able to use this test for that, but not this test for that. So it's not quite as clear, and it takes a little bit more work. Those standards have been in use for many years and have provided a lot of pipe and fittings that have done a lot of good jobs. So the standards are still relevant. They still do have value. Both of these standards also require the use of a bonding procedure specification and qualified bonders. So again, the new ASME NM2 piping code was written to address some of the deficiencies that are in each or other of the B31 standards. The B31-3 standard has a lot of good information in it, and so does the B31-1. They're not always the same. Sometimes there's more information in B31-3 for, say, thermoplastics again, than in the B31.1 standard. So the goal was to have NM2 be the repository for all of this information. And eventually, hopefully, the ASME NM2 standard would start to replace the references to B31 in the non-metallic piping codes. The ASTM specifications are more product specifications than they are specific codes or standards necessarily. ASTM D2996 provides the requirements for filament wound piping and contact molded piping requirements are shown in ASTM D6041. There are limitations to these specifications. 2996 is limited to piping size 60 inches and smaller. D641 only allows for piping systems up to 150 psi rated. And 6041 only allows the use of polyester resins. So there's quite a few things in these standards that limit their use. These specifications are primarily manufacturing specs with not a lot of assistance offered to a system designer regarding the overall design of the entire system. You have to have a better understanding of how to input these points basically into a stress analysis system. And there's very little guidance in either of the ASTM specs. They're not driven for that. ASTM D2996 does require the fabricator to obtain the hydrostatic design basis test for his pipe. ASTM 6041 uses more canned properties, more standard properties, because those are standard laminate types that are expected to be built. That's contact molded, hand applied, matte and woven unidirectional materials. So those properties are more well known because that's more of a repeatable, consistent laminate package. For ASTM D2996 being filament wound, fabricators commonly have differences in their fabrication processes, and those processes require independent testing of unique pipe. So that's why the testing is required. Now let's switch gears for a minute and try to talk about tanks and vessels. We're going to follow a similar format. There was 5 specifications chosen to review. Again, they're all different. They have strengths and weaknesses for all of them. I did not pick out any I would call regional specifications because I didn't have time. Honestly, you'll have to take what I've done here and compare what you do if you have a small regional specification and see which one works best for you. As with the piping specifications, each one of these specifications has strengths and weaknesses. And I always look at it like it's up to the owner or the owner's engineer or the owner's consultant to make sure that they use the right standards, that they include the proper piping standard and not ASME RTP1 for a piping job. I've seen that done numerous times, especially for quality requirements. And there are great quality requirements in the ASME RTP1 document, but that doesn't necessarily make them applicable to a piping job just because there's no good piping QA requirements in a code anywhere. So what are the similarities in all these tank and vessel standards? What do they all do well? Well, all of the specifications have design information. There are great differences in how those designs are approached between the specifications, and that's one of the differences in them. But in the end, they all provide safe equipment. They just have different approaches somewhat. And they all have fabrication requirements along with material handling requirements, because again, material handling is very important with fiberglass raw materials. So the ASME and the EN specification all provide information for product testing, and they have the QA/QC requirements and reference forms shown in those documents that the fabricator can use. They also allow for true certification and registration of a vessel with an accrediting body. With the ASME specifications for RTP1, that is a fabrication specification. So it's important to remember that once the vessel is fabricated and stamped and certified to be in accordance with the original requirements, that's what you're certifying. You're not certifying the vessel necessarily for future use, as you would maybe with a code vessel like a Section 10 code vessel, pressure vessel. So keep that in mind. These specifications all provide methods for developing laminate properties. Or, if it's possible, they give you the standard properties for the designer's use. And other than the EN 13121 document, the specifications provide little or no guidance for elevated vessel bottoms and how to reinforce those important appurtenances. Now, what's unique? What's different in them? Well, only the ASME and EN specifications allow for the certification of the tank or vessel with an accrediting body. The ASTM specs are primarily manufacturing specs, like we've talked. There's a big difference in the pressure ratings allowed by these specifications, and that's an important point that owner's engineers need to be aware of. Confirm the design pressure of your vessel before you select an incorrect specification. There's also big differences in the QA/QC sections of these specifications. Again, the ASTMs typically refer to other ASTMs which can provide good guidance, but only the EN 13121 and RTP1, along with Section 10, have QA/QC requirements shown in them, along with the forms and tracking documents and the items required to be done to produce a vessel to those standards. And again, only the EN specification provides good guidance for designing an elevated bottom. Let's get into each standard a little bit, like we did with the piping. So for ASME RTP1, it's one of the most robust and complete FRP vessel standards available. There are very few standards out there better than ASME RTP1 for common storage vessels. Now, they do have a maximum rating of plus or minus 15 psig. So if you need a 20 psi pressure vessel, this standard is not your standard. Standard also includes requirements for design, fabrication, and testing to be able to certify the vessel. This standard was first issued in 1989, and it is continuously upgraded, continuously modified. At yearly meetings, I mentioned before that I sit on the Materials and Quality Assurance Subcommittee for this document, and I can tell you that we meet twice a year to discuss vendor recommendations and user recommendations, whether there has been an issue found within the standard. And the standard is very good now. It's very robust. It's been through a number of updates, and it's quite widely used throughout the world. One of the best things of ASME RTP1 is the use of the user basic requirement specification. That doesn't just roll off the tongue, because we all just say UBRS. The UBRS is the intended design conditions, and it also provides information on what the vessel's to be used for, if it's going to be agitated, how it's supported. It's the information that the vendor needs to design the vessel properly. And this is all agreed to up front in the purchasing phase, so there are no questions, there's no confusions. And this is a document that follows the vessel throughout its life cycle. Certified ASME RTP1 vessel producers have to go through a rigorous process to be certified. They have to build a test vessel. They have to consistently be audited, and not just scheduled audits, but surprise audits to confirm that they're actually doing the paperwork, that they're actually following their design basis laminates. These audits happen, I believe, yearly, or at least they used to. COVID's changed the entire world now. But these audits provide proof to a customer, to you, if you're buying a vessel, that that vendor has met the requirements of ASME and continues to produce vessels that are in line with RTP1. It's a great system, and it guarantees you that your vendor has at least at one time been a very good vendor and can produce very good equipment. So the standard does require that a professional engineer certify the vessel's design. Now, one of the drawbacks is that this professional engineer has to be registered in one or more of the states of the United States or provinces of Canada, or alternately recognized by a jurisdiction outside the United States or Canada. This seems to currently limit the use of this standard throughout the world. It's not as commonly used throughout the world as it possibly could be. So it's a good thing that a registered professional engineer is required to review the design and confirm it, but it does limit this standard's use somewhat, I believe. When you step up to a pressure vessel, and a pressure vessel being, in this case, above 15 psi, and it's not being repetitively produced, there are a lot of pool tank filters that are built, and they're pressure vessels also, and they build a lot of them, and they're built the same way every time. But if you want a custom Class 2 pressure vessel designed and built to the Section 10 boiler pressure vessel code, you're restricted to a pressure vessel that's designed with the algebraic product of the internal pressure rating times the inside diameter. And that number can't exceed 14,400 pound-inches. Additionally, the maximum internal pressure cannot exceed 250 psi. And the inside diameter of a vessel certified to this code cannot exceed 16-foot diameter. So there are limitations. If you're going to have one of these vessels built, make sure you understand these limitations. This Section 10 standard is part of the ASME boiler pressure vessel code, and it was first published in 1968. It's an outstanding standard. It's been around a long time, and it is also constantly updated. Section 10 also meets twice a year at the same time as the RTP1 committees do, along with other meetings. This standard has very good rules for designing FRP flanges and for reinforcing penetrations. One thing to keep in mind is that, like with any other code pressure vessel that is stamped, if you have to make a repair, you have to make that repair using a certified Section 10 repair company in order to maintain the code stamp requirements on that vessel. And this would include any future modifications that you need to make to that vessel. Certification of a vessel to the boiler pressure vessel Section 10 code requires significantly more stringent testing requirements than other specifications. Often AE, acoustic emission testing, is required. These tests are intended to confirm the structural capacity of the vessel. As this standard is primarily concerned with the structural capacity of the vessel to not fail, the internal surfaces, the corrosion barriers, or the liners, the requirements for these vessels are not as well defined because the standard is primarily concerned with the pressure boundary, the pressure envelope, and not necessarily the liner. And it does have multiple classes of vessels shown in here, depending on if you're making the commodity type repeatable vessels or if it's a custom vessel. So you have to be careful when using this standard that you make sure you invoke all the right rules. To the EN 13121 standard. This is also an outstanding standard. It is divided into 4 sections that have requirements for raw materials, composite materials, and chemical resistance, where you set which materials you need, how to design and build the vessel, and then how to install it and deliver it. It has some of the most detailed design requirements of any of the specifications reviewed here. They are also some of the most complicated. That's a good thing because it helps minimize the walls, the thickness requirements for things, because the detailed design engineering is performed to prove that those things will work. But you have to be a very good engineer or understand FRP engineering very good to be able to use this specification correctly. Again, that's not a bad thing. It is just somewhat limiting. The EN 13121 standard does not pertain to vessels and tanks of irregular shape or underground storage tanks like the others. And this standard is applicable to pressure vessels that have a design pressure rating up to 10 bar. And there is another European standard that goes beyond that too. The EN 13121 standard is well reviewed now after being released in 2002. It's widely used in Europe. It is a very good standard that has detailed requirements for calculating the knuckle reinforcements at the transitions between the vessel structures. There's detailed procedures to obtain safety factors used in the design calculations, which again can be minimized through good data and good engineering. It's also been said by design engineers that this design standard yields the most optimized laminates. But again, You know, that's a good thing and a bad thing. If you know what you're doing, optimized laminates are very good. And it can produce some of the least expensive FRP vessels out there because of this. The ASTM product standards 3299 for filament wound and 4097 for contact molded vessels, again, are primarily product specifications on how to produce the vessels. The maximum allowable pressure rating for a vessel manufactured to these specifications is plus or minus 14 inches of water, roughly a half PSI. I often see ASTM specifications invoked for vessels that have 2 or 3 PSI design service expected. That's outside the requirements of this specification. So you have to understand what you're asking for and that it's within these specifications. These specifications also do not contain reference forms like the QA/QC reference forms that you see used in other specifications. And you can't certify vessels to these specifications. You can certify that they were built in accordance with them, but it's just the vendor certifying that he did the right things. It's not the same quite as independent certification by an accrediting body. Okay, one of the last things I want to make sure that you all know, with all of these specifications, some level of defects are allowable, depending on their placement within the overall laminate package. The closer to the service fluid that the defect is, you'll find more stringent quality requirements for those defects than the defects that are deeper in the structural layers. Regardless of which of these specifications you choose, and regardless of what you're having built, be it piping, tanks, miscellaneous equipment, or whatever, the quality requirements you expect need to be clearly explained in the purchasing documents. It's not enough to say fabricated, stamped, and everything in accordance with RTP1, because there's different quality levels allowable in RTP1. And your job is to complete that and tell the vendor what you expect. A vendor that understands what to expect will build you that typically. But if you don't make your expectations known up front in your purchasing, then it's a bad day for the vendor, because then they have to try to convince you what they want. And it's a sad day for an inspector when there's no QA requirements, because then we're just reporters for every classifiable defect. And I can tell you those reports are long and painful to write. So, wrapping it all up, I developed a quick chart to try to help myself understand some of the strengths and weaknesses of these specifications. I will tell you that these are all good specifications for their service. There's no reason to overqualify a vessel that doesn't need it. If you have a vessel that's required for a critical service, dangerous chemicals, something like that, you should invoke additional design and engineering requirements that are shown in the EN, the ISO, and the ASME documents. Typically, the more thorough and detailed the specification requirements are, the more expensive your equipment's going to be. That's okay, because if it's getting more expensive, it probably means there's something dangerous that you're storing. There's more to an equipment's value than just the initial cost of equipment. And one of the things I always try to highlight to people is in red there. If your equipment isn't in service, it has no value to you. If you're constantly having to bring a piping system offline because of a failure, it doesn't matter how little you spent initially to purchase that piping, because now your maintenance guy is going to spend the rest of that money across the next 5 years trying to fix it. So, one of the things I want to mention too in this is safety factors. Safety factors are different throughout each of these standards, and another entire presentation could be made on how safety factors are developed in each of these specifications. There are sometimes safety factors on top of safety factors. That's in part because of the limited knowledge in FRP laminates out there right now. So it's important that you understand how these safety factors are used in each of these standards. So when you invoke a standard, make sure you pay attention to that. Again, each of these standards has value. You just have to make sure that when you're the purchaser, if you're the end user, that you use the right standards to purchase the equipment that you need. If you have less knowledge, you probably want to err on the side of more caution for the standards. Okay. Now we come to the question and answer portion of the webinar. Daryl, is there any questions from the audience that you can start me off with? Maybe something simple?
Sure, yep. Thank you, Tom, well done. Some of these questions I think you may have alluded to, I may step in and add some of my thoughts on them, but first one here will be primarily for you. It was a little bit more specific, but I'll ask it more generally, maybe about visual acceptance criteria, comparing RTP1 with some of the other tank standards, and maybe as it pertains to NM2 as well. Maybe kind of just elaborate on that.
Sure. Yeah, that's a great question. And much like safety factors, the QA information in each standard is different. RTP1 has outstanding QA/QC requirements that shows limitations on air bubbles. So does EN 13121, and most of the actual codes and standards, the ASMEs and the ISOs and ENs, they have listed sizes of bubbles that are allowable depending on where they're at in the laminate. ASTM also has another standard, I believe it's 2563, that shows some allowable defects. But when you look at each of these standards, again, I think ASTM D2563 has 3 different levels of acceptable quality. So if you just say in accordance with ASME RTP1 quality, is it level 1? Is it level 2? Is there another level that you want to allow? Those are the important things that you need to remember with each of these standards, that you go into the standard that you invoke and you review the quality requirements so that you make sure you explain your expectations.
Okay. Next question, is there a code or standard that kind of governs or defines the design and manufacturing requirements for dual laminates? For pipes, that is.
Pipes, yes. There's not one specific that I'm aware of. There is rules being put into the ASME NM2 piping standard, but those are probably still at least one edition away. I happen to sit on that subgroup also, so I'm aware of the movement on that since I have to write some of them. But I'm not aware, Daryl, unless you know of another dual laminate standard out there that includes all this design and fabrication information yet.
Yeah, not that I'm aware of. There is a mandatory appendix 12 in RTP1 that has, I mean, it's pretty robust, right, for kind of dual laminate requirements on bonding and different things like that. So that is still kind of used. I can say the NM2 appendix will take heavily from there. You know, by and large, dual laminates, you know, the thermoplastic is just a corrosion barrier, so it's generally not considered as structural. So a lot of the kind of rules that are in M12 for RTP will still apply. It's just kind of going along for the ride. So you want, you know, the right material selection, just as if you're selecting a corrosion barrier. So yeah, you're right. There's nothing that I know of for pipes at the moment.
Yeah, the DVS standards for thermoplastics and some of the AWS thermoplastic standards work well standalone for just the thermoplastic side, but there's not a lot of good dual laminate information yet out there.
Right, and those DVS are kind of material specific too. I know there's polypro and maybe polyethylene, but not for every plastic either.
Right.
Okay, we can both talk to this one, but I'll let you start if you want. Is there a time you would use B31 instead of NM2? It sounds like NM2 would always be the better choice between the two.
Well, NM2 is probably a more robust document. It has more information for overall the entire non-metallic piping systems. and it is dedicated just to non-metallic piping. So again, B31.1, both of those have been in use for many, many years out there. They're in a lot of specifications, and a lot of the information, I would say, I think all of the information that's in those two specifications is in the NM2 specification. So the NM2 specification is just more specific to FRP, whereas the standard B31 specifications only include them as appendices or chapters. So it's a little more difficult to follow the B31 standards sometimes because they're driven for metals and then had plastics added in.
Yeah, and I'll add to that. I mean, it's a new standard. Eventually, our desire, and we will be giving, I mean, we have kind of a team set up to give presentations at different conferences to kind of promote NM2 more. It needs more awareness down the road. We feel there's a time that NM2 will completely supplant B31, but it's a new standard. So B31.1, I think, was first issued in the 1930s. It takes a little while to get awareness, a little time to gain universal acceptance. There are things that, you know, getting in the first edition of a standard, you try to get the main parts, and then you're going to build on that over years. So there's things like buried applications that are not in NM2 at the moment. There may be references to AWWA M45, B31.1, I believe, has kind of a buried design section as well. So eventually that will make it into NM2. We're working on that. The other thing that I would say is, for those doing pipe stress analysis, there are NM2 code stress equations in NM2 that have not made it in the pipe stress software. Just it takes time to get those code equations written. We have some people associated with Intergraph and Caesar in our committees that are kind of our liaison a little bit, and we're working to get those code stress equations. But at the moment, you cannot do an NM2 analysis because you're forced to use B31.1 or B31.3 or ISO code stress equations. So there are, you know, we need time to get those universally accepted and kind of programs written for that. And if anybody is interested in helping us with that, shoot us an email, because there are contacts. They basically need people telling them they want the NM2 code stress equations. So if you would like to do that for us, send us an email and we'll send you kind of the contact information that you can help us get more acceptance with that. Okay, this one's going to be for you. There's a couple more that I'll help with, but this is about kind of budget constraints on RTP1 vessels, as far as foregoing maybe a stamping requirement or foregoing maybe an acoustic emission test.
Sure.
Is it advisable? Kind of weigh in on that a little bit.
Yeah, I've always thought that, at least for me, and I understand that I see the world through my eyes, but quality has always been important to me. I'm one of those weird people. So it's always been important to me that things were built well. And so it's like safety. You want to be safe, but how safe do you want to be? So, okay, I'm going to invoke a safety rule, but I'm not going to say you have to cordon off your work area because, you normally do that. You wouldn't do that. But when people talk about this with the quality requirements, they always say, well, if we just don't get it stamped, it'll be cheaper. But you don't get the same tank if you don't get a stamped vessel. It's just human nature. You won't get the design package the same. The requirements are not the same. You may not get the same documentation at the end. So it's not equivalent if you say, I'm going to save 2% and get a tank that's designed and fabricated but not stamped, because you wouldn't do that with safety. And these vessels have a safety factor, a safety rating. And I've always thought that you were lessening your safety requirements when you lessened your QA requirements. And I've never been one to lessen safety requirements. So I personally don't like it. I know it's done. I just don't think it's a good policy.
Okay. I'm going to ask two and answer two, since these are
good. I'll mute
First
myself.
one, what standard would you recommend for anchoring design of tanks?
Oh, yeah,
So this is,
got this
yeah, so RTP1 has non-mandatory appendix for kind of hold down lug design and the influence that that has on the vessel itself. I know 13121 also has some equations for determining kind of uplift, overturning, that sort of thing. But if you're actually talking about anchoring into foundation, you're not going to find that in these non-metallic standards. You're looking at kind of local building codes, whether it's ASCE for that or IBC or different international kind of building codes for foundation design. Next question was, does the 15 PSI pressure limit for RTP1 include hydrostatic pressure? It does not. It's on top, so you can have a very, very tall vessel,
right.
and then you have 15 PSI internal pressure on top of that. There are cautions in RTP about kind of tall vessels and the effect that has on kind of, well, shell design, obviously, because it gets higher pressure, but also for bottom knuckle design. You know, there aren't really good rules for bottom knuckle design. So if it gets too tall, you want to make sure you do a higher level of analysis like an FEA on that bottom knuckle. But yes, the answer is it's hydrostatic pressure plus 15 PSI.
Right.
Back to you. Can you speak to the differences relative to the qualifications of inspectors associated with the different standards that you have researched?
Yes, well, some of the standards do require inspector not certification, but requirements. And it's different to understand also that there's a examiner and an inspector that's discussed in most of the standards. The examiner is expected to be the vendor's QC person who's going out doing the measurements, verifying the wall thicknesses, locations, things like that. And then there's the QA, the overview, whose job it is to come in and review the paperwork, review that everything is done right. So both of those things are kind of important. And I've lost my train of thought here, Daryl. What
Okay,
was our
well, I'll get you
question
on a
again?
different one that
Yeah, thank you.
I know you are directly involved with. I don't know how successful, but the question is, does RTP1 provide any insight on how to choose a quantity of limitations for gaseous air bubbles?
Oh my goodness, no, it does not. And you're right, this is a personal pet peeve of mine because I've tried to help committees work through some of these things and have not been successful so far. So no, there's not a lot of guidance. Fabricators can offer you guidance on what they typically recommend, and then you can review their recommendations and modify them if you like. You can also read the standard and come up with what you feel is a good, reasonable amount of gaseous air that should be included in your laminates or how big those bubbles should be. But no, the vendor who purchases the equipment needs to specify that, and they need to review the document first to find out what they have to specify.
Yeah, and to add on that, I mean, these committees are made up of engineers, owners, manufacturers, consultants, which is good. You get everybody's opinion, but that makes it difficult to find common ground on a lot of these areas because an owner is going to want to be stricter than a fabricator. So
Right.
until we have kind of universal agreement or do something, you know, based on maybe how aggressive a chemical is and kind of standardize that a little bit more, it's hard to have just a simple rule of, you know, this many air bubbles per square inch or square foot. So that's kind of
Right.
why we've had difficulty coming and agreeing on a common ground for that.
Yeah, thank you to whoever asked that question, though, because that is a pet peeve of mine when people invoke these standards but then don't finish the job. So that's the last part of it.
Okay, we have about 4 more minutes, so I think I can go through a couple more questions here. This one, maybe we'll see how it goes. Why don't we have an international standard for FRP? Do we feel
Yes, I
RTP1
agree.
is better than the other standards, or why couldn't we have just an international standard?
See, better is ethnocentric, and my better is not better to someone else. That's the problem. I live in my world, and someone else lives in their world. When I was young, I thought I knew the entire world because I knew everything around me. As I've gotten older, and thanks to the interweb, I realized that the world is bigger than I thought it was. And there's more people out there, and all of you shouldn't be beholden to what I require here. It would be great if we had an international standard that was global. It would also be great if we had global love and kumbaya. But I don't think either of those are going to happen. I think we can try to harmonize standards and find common ground, but even the standards that are out there, for instance, the EN 13121 and PS 1569, have different methods, have different ways that they do things. Typically, I believe they all end up with similar properties and similar requirements, but they have different ways. And for me to tell the people in Germany or China or Saudi Arabia that my way is the best way is very difficult. And I don't think it'll ever happen. So I think we're going to have numerous standards internationally as long as we go forward.
Yeah, and there's a practicality to it, right? I mean, we not just being Americans, but we want to have influence over, what we are using.
Sure.
So there's it's difficult to travel to Europe to sit on these committees and offer your insights. So everybody has things that are important to them. So
Right.
it's just like building codes, how California has a different building code than Florida does because of what's important to them. We have our standards written around what's important to us. Yes, there is some borrowing from standards. We're not reinventing the wheel in a lot of these
Sure.
situations. So each standard has kind of universal equations or approaches, but there are certain things that are more important to us that we want to have a little bit more control over, as in North America.
Right. Well, and that's a good point because people in Chile fear earthquakes much more than people in, somewhere else, say Australia.
Yeah.
And people in Australia would fear something else. So
Spiders.
spiders.
Okay, we have about 1 more minute. And just know that when you're answering this question, because it can go on. But which would be the best recommended specification to inspect piping or vessels once they are in service?
Well, the ISO standard, I believe, has some information in it. I have not read all of it, so I can't speak to it deeply regarding maintenance and after installation. Most of the standards, though, typically stop at installation. That's where their requirements end. There is good information in ASME NM2 and ASME RTP1 for quality that can be used in other areas, like for a follow-up review or a follow-up inspection. You can't necessarily invoke those codes because they're, again, RTP1 is a design and manufacturing code. Once the vessel's built, it's complete. But you can say in accordance with the standards, the quality standards in those standards. I don't know of another good way to do it, though. Invoke
Okay.
your own standards with your own company, perhaps.
Okay.
All right.
Well, I think we made it through them all, and why don't you take us home?
Thank you, Daryl. All right, everybody. 1 quick minute here to give a shout out to the next Maverick webinar we have planned. Daryl gets to be on tap next. He's our chief engineer, and he's going to provide you with something scintillating engineering-wise that will no doubt leave you in awe of his brilliance. And finally, because this is my webinar, I get to share pet peeves. Share what you learn within your companies, within your peer groups. Heck, tell your kids. Being the smartest person in the room is worthless if you just sit quietly in a corner. Unless you're willing to take what you learn and share your lessons with others, nothing's ever going to be gained from it. So share your knowledge. It's my recommendation. That's it for this webinar. Thank you for taking a few minutes out of your time and spending it with me. I do appreciate it. I really do. Feel free to reach out to me in the future if you have any non-metallic equipment inspection questions. That I know pretty well, and I'm glad to help. Stay safe, everyone, and take care.